All right, so last time, so we considered the case when our training error is very small, right? So we had almost zero training error, and in fact, in many practical deep learning implementations, this is in fact the case. So when our training error is zero, so we are in basically the interpolation regime. So what do I mean by that? When we have training sets like xi's and yi's, 1 to n, so I want to be able to interpolate my relationship, the relationship between x and y. So I want to learn a function f with parameters w such that if I apply this function over my input xi's, I would get my labels yi for all my training samples. So we abused a little bit of a notation and we wrote these systems of nonlinear equations like fw is equal to y. So x here is implicit and w is the parameter vector, m-dimensional. So we have m parameters, and y we assume lives in an n-dimensional space. And when we say the system is over-parameterized, we mean m, the number of parameters, is larger than n, the number of samples. And here, this small n, when we are in a multi-label classification or regression problem, would be equal to the number of samples times the number of classes that we have. So this is the number of samples that we want to interpolate, and these are the number of parameters that we have in our model. And we saw some examples that the solution of the interpolation may not be actually unique, right? So let's say you are in a three-dimensional space. Let's say this is the manifold of all of the w's that satisfy your first equation. When you apply your model to x1, it will give you the exact label y1. And let's say this is the other one. When you apply your model to x2, you will get y2, and the intersection would be the manifold of my optimal w's, w stars. And in fact, they are not isolated, and that's one of the differences between over-parameterized and under-parameterized regime. So in order to find these solutions, we define a loss function. Mostly we use the quadratic loss because it is easier to analyze, but some of the arguments that we covered, in fact, can be applied to other loss functions. And we minimize this loss function using gradient descent. And we want to understand, or a stochastic gradient descent, and we want to understand why gradient descent in this regime finds a good solution, W star for us, that can exactly interpolate the input-output relationships. That's basically the whole idea of the previous lecture and today's lecture. All right, in order to understand this, remember, this loss function, in fact, can be non-convex, right? So if it was convex, we did not have any issues. So this loss function can be non-convex. And in fact, it is what we showed, it is essentially non-convex. Even in a local region, the Hessian can have positive and negative eigenvalues. So even locally, it is not convex. So one very important condition that we discuss in order to show the convergence is the PL condition. So we said a loss function or any function satisfies the PL condition if I look at the magnitude of my gradient, the magnitude squared, is greater or equal to a constant mu times the value of loss function for, let's say, all W in a particular region that I'm considering. All right, so if my loss function satisfies this inequality, then I would say that loss function satisfies mu PL condition. And at the end of the previous lecture, I stated the exact theorem that when we have the PL condition, we would get convergence of gradient descent under the assumption that our loss satisfies PL condition and some other assumptions. All right, so today, first I'm going to give a little bit of an intuition what is going on with this PL condition, right? So you have like the magnitude squared of the gradient greater or equal to a constant times the loss value. What is going on here? So why do we need this condition in order to say something about the convergence of gradient descent? Okay, so let me pause because I see a few questions. So there is a question about the isolated and non-isolated optima with respect to the manifold. When we are in a non-isolated fashion, let's say you basically have 2 points, so there is a path connecting the 2 points, that all points on that path, they're also optimal solutions for my optimization. But when you are in an isolated fashion in the under parameterized, then you may have one solution here, but the neighborhoods of that solution won't be an optimal solution for the optimization. All right, so the other questions are about logistics. I'll have an office hour after today's lecture. Maybe you can ask again those questions in that office hour. I'll be happy to answer those questions. Okay, let's move on. All right, so what is the intuition behind the PL condition? So we want to see, in fact, this condition, even though it may look a little bit strange at the beginning, this is really, really intuitive and very simple, condition that immediately leads to the convergence of gradient descent, even in non-convex cases. All right, so basically the assumptions that we have here for the loss function. So here we are assuming my loss function in a ball that contains the trajectories of gradient descent. So that's something I'm gonna discuss in a little bit. So this loss function is mu PL. So that's the PL condition. We also assume it is beta smooth. It means the Hessian, the eigenvalues of Hessian are bounded by a particular number, let's say beta. Again, Hessian doesn't have to be PST, so we just need the bound on the curvature values. That's all. And we also had an assumption on the learning rate. So obviously your learning rate cannot be very large, because in that case, even in the convex setting, the gradient descent, we don't have a guarantee of the convergence, and we are assuming the learning rate, which is eta, is sufficiently small. Let's say it is 1 over beta, the largest eigenvalue of your Hessian. So this is the learning rate. So these are roughly the assumptions that we have. The beta smooth assumption in the convex setting, again, in the proof of the convergence of gradient descent in the convex setting, we have some bounds on the values, eigenvalues of the Hessian, even though we are in that case assuming the Hessian is PST. We also have a learning rate, the assumption on the learning rate that it should be sufficiently small. So the extra assumption that here we have is that instead of like convexity, we are assuming the loss satisfies the mu PL condition. And we are basically going to analyze the dynamics of gradient descent, where WT plus 1 is equal to WT minus mu times the gradient of our loss at WT. And we want to see if the dynamics of gradient descent would take us to the global optima. Okay, so the first step here, and perhaps a geometric interpretation of the PL, comes from just Taylor's expansion. It is quite simple, kind of, resembles the proof of the convergence in the convex setting with some differences. All right, so we look at the Taylor's expansion around, let's say, WT. I'm going to expand my function and I'm going to evaluate my loss at WT plus 1. So in that case, I have my loss at WT plus 1 is equal to my loss at WT, right? So what is the second term? We have WT plus 1 minus WT transpose times the gradient. This is the first order Taylor's plus half WT plus 1 minus WT transpose times Hessian at a point, let's say W prime, times WT plus 1 minus WT. It's just Taylor's theorem. All right, so let's replace the terms that we know what they are. So what is WT plus 1 minus WT? I'm using gradient descent. So WT plus 1 minus WT is equal to minus mu times the gradient. Right? So wherever I see WT plus 1 minus WT, I'm gonna replace it with minus mu, the gradient vector. And same here, minus mu, the gradient vector, minus mu, the gradient vector. Okay. So, and there's a transpose here as well. All right, so another assumption that we know, even though I don't assume my Hessian is PSD, I know the maximum eigenvalue of the Hessian is less or equal to beta, right? And we know, let's say if you have a vector Z transpose times a matrix times Z, this quantity is always less or equal to lambda max of my matrix times the norm squared of Z. First, we are going to use that result to have a bound on the right-hand side of this equation. So this is going to be less or equal to, right? So I have a loss here. So what about this term? I have minus mu gradient transpose times gradient is the norm squared of my gradient. All right, so let me actually do this part in 2 steps just to make sure that everybody follows. So here I have the mu's, they are constants. So I have mu squared over 2. So I have gradient transpose times this Hessian matrix times the gradient itself. So and because the lambda max of Hessian I know is bounded by beta, so this whole term is bounded by beta times the norm squared of my gradient. So then here I have, if you look at these terms, I have norm squared of the gradient, and here I have norm squared of the gradient. Of course, I have these constants as well. So if I put everything together, so I'm gonna get a term like this. So it's gonna be less or equal to, I have my loss at WT. So I'm gonna factor out from, factor out mu times the norm squared of the gradient. So here I'm factoring out this. So the, so I think I'm making a notational error. So my learning rate is in fact not mu. My learning rate is eta. Mu is the constant for the PL condition. Okay. So let me see if you guys caught that in your messages. That was a test to see if you guys are all awake. Yeah, I see one comment about it. That's great. So at least one of you was awake. All right. So the good thing about the tablet is that I can just erase these things. So, okay, I have eta here, I have eta here, I have eta here. Okay, then I have minus eta here, eta times eta, eta squared. Perfect, okay, good. So then I'm going to basically factor out minus eta times the gradient. So here I'm gonna get 1. So what about here? I'll have minus eta times beta over 2 for the second term, and then I factor out the square norm of my gradient. So that's it. So this is basically Taylor's expansion. So what I used so far I used the bound on the maximum eigenvalue of my Hessian. So basically I used the second assumption that my loss is beta smooth. So let me use my third assumption. When my learning rate is small enough, let's say 1 over beta, then in that case, or smaller than that. So in that case, this is, let's say, 1 over beta. So here you get 1 over half. So this whole thing is going to be less or equal to WT minus half times the gradient, the norm squared of my gradient. That's it. So basically I use my third assumption here. I use my second assumption here. I haven't used my PL assumption yet. Okay, so I hope that all of you immediately sees what is going on. Why do I need a PL assumption? Right, so far I basically used Taylor's expansion. I used the beta smoothness of my Hessian to have a bound, and I used the sufficiently small learning rate in order to bound this with a constant number, let's say half. So I basically end up with this inequality. So let's think about it. It says my loss at the WT plus 1, the parameters when I update using my gradient descent is less or equal to my loss at the previous time. That's good. What is the amount of the decrease in the loss? So this guy is a bound on the amount of the decrease in the loss value, right? So if this amount is big enough, that is good for us, right? So we want to make sure that in each step I substantially reduce my loss value. And one of the really good bounds for this amount would be the case that the amount that I'm reducing is proportional to the value of the loss itself. Let's say if my loss is like 100, if I could reduce in every step, say 5% of the loss, then I would have a geometric decrease of my loss value, and I would converge to a 0 value of the loss. And that's exactly the underlying assumption of the PL condition. Because if you recall in the PL, so recall in mu PL assumption, what we have is that the gradient at a point, let's say WT, the norm squared of that is larger than mu times the value of the loss, right? And here you can see we have this amount of the decrease of the loss in each iteration of gradient descent, in fact, is bounded by, let's say, 1/2 the norm squared of my gradient. And I want this value to be large because I want to decrease the value of my loss significantly at each step. So if you apply this inequality, let's say you have used the mu PL, the first assumption here, you can immediately see then we have a bound in this sort. So we'll have this to be equal to loss at WT, but this guy is less than mu times WT. So the whole thing is going to be less or equal to eta times mu times W loss at WT. So I can just factor out from WT, loss of WT, so I'll get 1 minus eta times mu, right? So in other words, under the mu PL assumption, what I get is that my loss at WT plus 1 is less or equal to, let's say, 1 minus eta times mu, my loss at WT. I'm reducing the value of the loss with a constant percentage. Let's say, at every step you are reducing it by like 5%. And that's fantastic because you can immediately see that your loss at iteration t is less or equal to 1 minus eta times mu, this is a constant number, to the power t times your loss at 0. Right, so you just apply it recursively. So you have a loss at 0, your loss at 1, W1 is less or equal to this constant 1 minus eta times mu times loss at 0, and then just you repeat that. So you'll basically get a geometric decrease or an exponential decrease in the value of your loss function. And that's it, that's the convergence of the loss to basically a 0 loss. And your convergence rate is, you can see, is dominated by this number. So if this number, let's say it is like 1/2, so you will get 1/2 to the power t, your loss at 0. And it's a very fast rate, right? So at every time you are, if your loss is 100, in first iteration you go to 50, in second iteration you go to 25, in third iteration you go like, almost 12, and so on and so forth. So you have a very fast decrease in the value of the loss function. On the other hand, if this number is very close to 1, let's say if this is like 0.9999, when you have a bad conditioning, that's basically what we argued. So then the decrease in the loss is going to be very, very small. Right? So you basically have like, you need, to wait a long, long time in order to get a small loss value at the end. So that's basically the rate of convergence. And this is, in fact, kind of proof and also the intuition behind the PL. Right, so then you don't actually see PL as like this abstract condition that came from nowhere. It is basically Taylor's expansion. You have a bound on the amount of the decrease in each step, and then you just want to have that amount of the decrease to be proportional to the value of the loss function in order to get a geometric decrease in the value of the loss. Okay, so let me pause here because I see there are a few questions posted. Okay, so there is a question. Is there a way to control mu? Very, very well. So I'm gonna talk about that. In fact, that's one of the main challenges because, here we are proving something very generic, right? So we are saying if I have these assumptions, then I have a convergence. But if you give me a neural network, can I show these assumptions hold? So that's something that I'm going to talk a little bit later in today's lecture. So there's another question. Wouldn't faster changes in the loss value lead to larger changes in the weights and make the training unstable? No, right? So because here we are assuming the loss is beta smooth, right? So in other words, there is a bound on the curvature values of the network. So it won't be the case that if you change your loss a little bit, then your parameters are going to like change in a crazy way, because in that case you would have needed a a very high curvature value. But at the end of the day, what we care about is to have a model that achieves almost zero loss function. Okay, does it mean the PL condition always does not hold for those laws whose global minima is strictly positive? That's a good question. So here we are showing just one direction, right? So we basically showed if we do have the mu PL condition, we have a convergence. I'm not sure if the converse is true, right? So if you say like if you don't have a convergence, does it mean that you are violating the mu PL condition? Because we have some other assumptions, like so it may be the case that your learning rate is large, but then the question is if you assume your learning rate is sufficiently small, if you assume the loss is beta smooth, then does it mean if you don't have a convergence, does it mean you are violating the mu PL condition? That's a good question. So maybe. So I don't exactly know if that's true. Intuitively, it makes sense, but I'm not quite sure. All right. So I'm really happy that some of you answer others' questions. That's great. I like, you to interact with each other, even though we are in a more virtual setup. Okay, so what about the higher terms? So in the Taylor's expansion, I just use the Taylor's theorem that I can replace the middle term with W prime. So that's exact. And we know like a global bound on the Hessian eigenvalue. There may be the case that you may have higher order terms and you may come up with a better convergence rate. So we are not looking into those analyses. So there's a question, the condition won't hold for ReLU networks because of non-differentiability. I think almost all of these, even though we are assuming everything is smooth and stuff, I think almost all of the arguments can be extended to ReLU networks because the set of non-differentiable points are measure zero. But I think that probably needs a little bit of a more careful analysis. So let's assume everything is smooth and nice and differentiable for today's lecture. So I'll let you guys work on the the case when you have a measure zero non-differentiable models. But I'm pretty sure that almost all of these arguments hold in those cases as well. And the other paper that I posted, probably we won't have time to go deep into the details of the other paper that analyzes again over parameterization in a neural network that's in fact specifically for ReLU activation. So that gives me a little bit more certainty that these results hold for those cases as well. Okay, so when eta is high, the learning rate is high, so you cannot even prove the convergence in the convex case, right? Because if your learning rate is high, you may be jumping around your optima. So that's basically a sensible assumption to have here. Okay, so let me move on. All right, so that's basically the idea behind the convergence of gradient descent under the PL condition. But here we have actually a technical caveat. So something that I didn't mention. So the technical caveat is that we are assuming that we have a ball. Remember the radius of the ball that we stated. So in the ball with the radius less or equal to 2 times 2 beta loss at 0.0 over mu, basically our ball is all w's whose distance to w0 is less or equal to r. And we assumed because in order to say that, okay, the mu PL or the smoothness conditions they hold, we should say they hold in a specific, ball with some specific radius. So one thing that we didn't show is that when we are doing gradient descent, we may get out of this ball, right? So even though I'm assuming, okay, I have all of my conditions are satisfied in this ball, in fact, I may get out of it. Right? So you start from W0, you go to W1, you go to W2, let's say WT. Right? So let's say you have this ball. So one part that we need to also show is that we are going to remain in this ball using basically by using gradient descent dynamics. But there is an interesting trade-off is in fact happening. If you basically look at the length of one of the octates. So let's look at between WT plus 1 and WT. So what is this vector? This vector is basically proportional to the gradient at WT, right? Eta times the gradient. So the length of this vector is therefore what? Eta times the length of the magnitude, the norm of my gradient vector. All right, so in order to say I'm gonna remain in this ball, then if I need to sum up all of the length of these octate vectors, right? So here I have eta times the gradient at 0, eta times at gradient 1, and here I have eta times gradient at WT, and to the basically convergence to the infinity. So I need to sum them up, and I need to show that if my R is a number like this, I'm going to remain in this ball. So in order to do that, I need to have what? I need to have an upper bound on the length of my gradients, right? So if the magnitude of my gradients are large enough, if this is like say very large, so then I'm probably going to get out of this ball. So I need to have an upper bound on the magnitude of the gradients in order to say I'm going to remain in this ball. So basically I want to say the magnitude of the gradient is less or equal to something, and then I'm going to bound the sum of these upper bounds and show that I am going to remain within this ball. But you see there is a kind of trade-off here, right? With the mu PL, if you recall, so I want to have a lower bound on the magnitudes of my gradients, because the magnitudes of my gradients, they show how much I'm decreasing the value of my loss function, right? So larger mu is better for me. But here, if I have a large magnitude, then I need to satisfy these mu PL condition in a much, much larger radius, in a larger ball. So there's this trade-off, going on between these two terms. Okay, so this part is also pretty straightforward to bound. So these bounds then are like kind of, technical. So you may actually come up with some other ways to, bound these terms to have like, better trade-off between the radius and, the convergence rate. So we'll do like we'll basically follow again the Taylor's expansion in order to do that. So let's look at this part. I'll call this equation star, inequality star. So here, this tells me the square root of the norm of the gradient. I haven't used the PL, so I'm just looking at this part. The squared norm of my gradient is less or equal to 2 over eta, the difference of the loss at WT plus 1 minus WT. And then you can use that. I'm not going to go into the details of that. You can use that and show that if the radius is set to be this number, then even after infinite iterations using this dynamic, we are going to remain in this ball. So one thing to note is that here we have mu in the denominator, right? So again, that's the trade-off. So if your mu is large, it means you are decreasing faster, but here your radius is also going to be smaller. And then if your mu is very small, you have a bad conditioning, then your radius is going to blow up inversely proportional to the mu. So it is very straightforward. So this part, just to save a little bit of time, because in today's lecture I want to finish this over parameterization argument. So I'll let you to read the proof in the paper. Okay, so let me pause here. I see a couple of questions. W0 and R. So did I? Yes. So good. So I can say Phil is awake. So this should be W0. Okay, good. Now the question is, okay, so far what we have shown is that under the assumptions that we had, right? So we have the mu PL, we had the smoothness and like the sufficiently small learning rate. So we do have a convergence of gradient descent for any general nonlinear system, right? So we did not assume anything particular about neural networks so far, right? So it could be, the same argument for other systems as well. So the question that we'll look into in the rest of today's lecture is, why neural networks satisfy the conditioning, these assumptions that we have. So why neural networks satisfy the basically conditioning assumptions. That we have. It means like the mu, we have a mu PL condition and we have like a bound on the curvature value. So there are different ways to think about it, and I can say that none of these, ways of thinking, they're definite. So there may be some other and better ways to understand conditioning of nonlinear systems that are more generalizable. But one way to think about it is that if I have a control, Hessian control, then I can show the conditioning will hold in a ball around my input. So first, let me in a high level explain what I mean by that. So remember, the mu PL condition is equivalent to show that the minimum eigenvalue of my tangent kernel is bounded away from 0, right? So this tangent matrix, tangent kernel, is a PST. But if we show the minimum eigenvalue of it is bounded away from 0, then we have the PL condition. But perhaps, this is hard to show in every W in a ball around my initialization, right? So if I show that maybe when I'm randomly initializing my my weight, I satisfy. So please mute yourself, when you are not asking a question. So if I could show that this is being satisfied at my initialization point, at W0, right? So that's something I can do, because let's say I'm, going to start with a random normal initializations, and then I know how to compute, characterize my tangent kernel for a particular neural network, and then this is something I can do. And then if I could also show that there is an upper bound on the eigenvalues of my Hessian in a ball, right? So within a ball, let's say I can show the maximum eigenvalue of my Hessian is bounded, right? So here we are relaxing one of the assumptions. Before I assume the eigenvalues of my Hessian are bounded in a ball, and I also assume I have the mu PL, condition also being satisfied in a ball. Here I'm saying, okay, maybe this is harder to compute, so I'm gonna just show this is being satisfied in my initialization, and then I have a curvature bound within a ball. Then there is a hope, right? So why there is a hope? So this tangent kernel, if you remember, it is basically the gradient times gradient transpose. Right? So it is basically gradient times gradient transpose. And this Hessian is the rate of change in the gradients. Right? So Hessian is like the double derivative. If I have a bound on the eigenvalues of the Hessian, it means my gradients, they don't change too fast. Therefore, maybe I can use that in order to argue that if I have a mu PL condition at my initialization, I'm going to also have a mu PL condition within a radius of my initialization. And that's basically the key idea of the Hessian control. And I would say a lot of recent papers talking about overparameterization in neural networks, they basically use this argument. And you can see, obviously, this argument has some limitations, and I'm going to talk about the limitations of this argument later on. All right, so let's go with an example. So let me take a look at the time. Okay. Example. Let's consider the simplest example when we have just one hidden layer. Let's say my input is in one dimension. This is the simplest possible example. I have one hidden layer. The weights are W1, W2 to Wm. And I have my second layer. The weights are V1 to Vm. And this is my output Y. Right? For the simplicity of the argument, we are going to assume these weights are fixed. And they're uniformly sampled either from +1 or -1. Right, so the results can be extended to the case that you are optimizing the second layer weights as well. So if you look at a lot of recent overparameterization results, this is roughly speaking the setup that they start, and then they extend the results to the case when we are optimizing over the weights of the second layer as well. But nevertheless, this is a good example just to build some intuition. And in fact, because these weights are can be positive and negative, we'll end up with a non-convex optimization problem. Okay, so what is the output? Say for a given x, we have, I'm gonna use a scale version of it. So 1 over square root of m. This really doesn't matter. It is just to make the notations a little bit simpler later on. Some 1 over m. So we have vi times my activation, let's say sigma, times wi times x. Right? So for each path here, so you have wi times x, you apply activation function. Again, another thing here is that we are assuming there is no bias term, right? Just for simplicity. And I multiply with vi. Right? So let's ask this question that if we can show, can we prove the convergence of gradient descent prove convergence of gradient descent for this very simple neural network. Right, so we had a big general theorem, and we want to see if we can, for know a particular neural network, we can use that theorem in order to show the convergence of gradient descent or stochastic gradient descent. So something I should have mentioned here, even though we mentioned the results for gradient descent, similar result holds for stochastic gradient descent. The proof is a little bit more complicated, so I'll refer you to look at the paper for the proof. Okay, so in order to do that, again, we need to understand the Hessian and the tangent kernel. Right, so there are two matrices. Remember, one is K and the other one is the Hessian. So we need to understand these two things. So in order to first look at the tangent kernel, we need to compute the gradient. So I'm going to compute the gradient of f with respect to, let's say, particular wi evaluated at x. Right, so what is the gradient with respect to that, with respect to, let's say, wi here? So we'll have vi times x, the gradient of the inside, times sigma primes wi times x. So it's a very simple gradient computation. Vi times x times sigma prime wi times x. And then my gradient vector would be a vector whose ith component is this guy. So this is a scalar, right? So I'm gonna put all of these components and I'm gonna have a vector of m dimension for my gradients. All right, so then what is the tangent kernel here? So this is for a particular x, this is gradient of f transpose times gradient of f. So this will be a particular number. So let's say we are evaluating just for a diagonal term, right? So remember, this tangent kernel is an n by n matrix, and n is the number of samples that I have for each pair of samples. So I'm going to compute the tangent kernel. So here I'm evaluating just the diagonal term. I'm taking x and I'm taking x. I'm evaluating this tangent kernel in the between 1x and itself. So in that case, it is basically just multiplying the gradient with itself. So I'll get 1 over m and summing up over different components. So here we have 1 to m, vi squared, x squared, sigma prime wx squared. So I would definitely encourage you to do these calculations at home for yourself. So these are very simple calculations, but build some muscles in order to do some of these derivatives. Okay, so we assume vi's are fixed, either +1 or -1. So vi squared is going to be always 1. We have, let's say, an activation sigma whose derivative is bounded, sigma prime, let's say, bounded by a constant number. And let's say I have x's whose magnitude is also like bounded with some constant number. So these are pretty fair assumptions. So in that case, I'm like summing over m numbers and dividing by 1 over m. Right? So this guy is going to be like order 1. It won't depend on M. So I'm using some hand wavy argument here. So that's the diagonal of my tangent kernel. So as I mentioned, this tangent kernel is an n by n matrix. So I know the diagonal elements, they are order 1, right? So they are not increasing or decreasing by m. So if I look at the trace of this kernel, what is the trace? So, okay, so the trace will depend on n, but I don't care about n. So the trace will be independent of my number of parameters. So it will be order 1, right? So here I just want to look at the dependence on the number of parameters, because that's something that I'm gonna like, you know, push it to the infinity in the over parameterization. All right, so the trace is also like order 1, and we know the eigenvalues are bounded by the trace. So in fact, if I look at the eigenvalues of my tangent kernel, this will be order 1. Right, so that's basically a kind of a hand wavy argument, but you can in fact make it very precise quite simply. So that's about my tangent kernel. Right, so in order to show the convergence, I need to think about tangent kernel matrix, and I also need to think about the Hessian matrix. So similarly, you can compute the Hessian. Hessian will be a matrix m by m. And the ijth value, so here we compute the gradient with respect to wi. You compute the gradient of this with respect to wj. You will get the following expression. Quite simple because everything is one-dimensional. Wj times x, x squared, indicator when I is equal to j. So the Hessian is going to be a diagonal term here. So you are not going to have an off-diagonal term. Why is that the case? Here, if I want to compute the gradient with respect to wj, there is no dependence on wj, so you're going to get 0. So the only terms that will remain non-zero, they'll be the terms when I is equal to j. So Hessian is a diagonal matrix. And it is even simpler because in a diagonal matrix, the elements on the diagonal, they are the eigenvalues. So if I look at the spectral norm of my Hessian, which is the maximum eigenvalue of my Hessian, I can just look at the maximum of my diagonal elements. HII, and this is basically x squared over square root of m. Again, I assume vi is 1 for the max, and I basically get a max over I vi is sigma double prime w times x. All right, so let's look into this. Again, let's say the curvature, the sigma double prime is bounded by a number. I know vi's are either +1 or -1. So this is basically a constant. So again, we assumed x has a bounded norm. So this is a constant. So the only thing that depends on m here is this guy, 1 over square root of m, and that doesn't go away. So this whole term, therefore, is 1 over square root of m. So what do we have here? So we have Hessian going to 0 as basically my m goes to infinity, and my tangent kernel remains constant. Right? So that's basically the kind of hand wavy calculations that we did, but you can see this can be made very precise quite easily. So as m goes to infinity, my Hessian goes to almost 0, right? Because this goes like with 1 over square root of m. My tangent kernel is going to something constant. And here we have the Hessian control, right? So because Hessian tells me the change in my tangent kernel. So if I show that my tangent kernel satisfies the mu PL condition, then I'm pretty good because I can use this argument to show that it will have the mu PL condition in other parts of my ball, and my Hessian also has a bounded eigenvalues. So therefore, with the Hessian control, I immediately get convergence of gradient descent or stochastic gradient descent. This is really simple, but kind of, interestingly, a lot of overparameterization results that have been recently out, they're in fact based on this intuition, right? So what they do is that they have a bound on the eigenvalues of the tangent kernel in the initialization, because that's something that we can do. And using the Hessian, using bounded the curvature values, then basically I can show the gradients, they don't change too rapidly, so I'll have the mu PL later on in other parts of my ball, and that's it. I can use that in order to show gradient descent or a stochastic gradient descent. But here there is a little bit of a catch, right? So that's something I I don't personally like, because I don't think, in fact, this explains why neural networks and why deep learning works well in the overparameterization setting. So the catch is the following, right? So, okay, so yes, you have a Hessian control. Your Hessian approaches, to zero in very big models, and your tangent kernel approaches like something constant. But in fact, what you are basically arguing here is that in a large model, your model approaches to a linear model, right? Because Hessian is the curvature of your model. When Hessian goes to zero, it means your model is almost linear, right? And then if your model is almost linear, then I knew from the very beginning that linear model with a convex loss, then I can have a convergence of gradient descent and a stochastic gradient descent. So that is one limitation of these types of arguments, because even though it is very precise and it shows precisely that in the limit, we'll basically approach to these almost linear models, and we use those results in order to show the convergence. But in fact, there are some works that they show there are limitations for this type of thinking in deep learning. So this is not very good, right? So this doesn't fully explain what is going on in the overparameterization in deep learning. All right, so how can we think about this problem? Before I take questions, so let me just add one other comment, that the same argument that I mentioned with the Hessian control, you can extend it to an L layer network, layer neural network, and then there you can show that if M is bigger than like the number of samples divided by mu to the power, some other terms here, then again, you have the Hessian control, right? So you'll basically have very small variations in your curvatures, and then you'll have a control on the tangent kernel in a ball around your input that takes you in the the trajectories of gradient descent, and use the results in order to show the convergence. But again, these results also have this kind of issue that in a way, in a large system, we are linearizing the system. And in fact, I don't think that explains the full picture. Okay, so let me pause and take some questions. I saw one hand was raised. Please go ahead.
Yeah, hi, Professor. Can you go to the previous page? So the equation K W of x comma x, is that the equation of the trace or the individual diagonal element?
So this is the individual diagonal element, right? So I should have written perhaps, let's say this is xi for a particular sample, right? And then, oh, not xi because I'm using I here. So I'll use xj. And then it will be a particular element on my diagonal of the tangent kernel.
All right, thank you.
Right, sure. So let me read some of the messages and questions here. Okay. So why are we considering the diagonal elements? Because the trace of the diagonal elements, that's one way to bound the spectral norm. So because the trace is the sum of eigenvalues, so we use that technique in order to bound the spectral norm. But you don't have to use it. You know, in other cases, if you can have a better bound, that may work out. But here it was sufficient for us. Okay, good. So there's a question, where could I find previously recorded videos? It's on the course web page or on Elms. Either way is fine, or it's on Twitter. So I, sometimes, post some of these, lectures on Twitter. Okay. Right. So even in the other paper that that I posted on the course web page, it has some results in the same flavor. Right? So if your m, the number of parameters is larger than a certain, so here m is basically the number of neurons in each layer. So there are some differences with the m that we consider. Take a look at the paper for the exact definition. But if the number of parameters is larger than some functions of the number of samples, then we have convergence of gradient descent. But some of them are a little bit, not completely satisfying. As I mentioned, basically the gist of the argument is that in the limit we are approaching a linear model, and because linear models we know the convergence, then we can prove some sort of convergence of non-convex optimization of deep learning in the over-parameterized setup. But the approaches that we talk, the conditioning, is in fact not limited to this view of linearizing the model, right? So we can look at one example to see, in fact, the approaches that we have talked, they're more general than some other results in understanding over parameterization. All right, so let's look at an example. Okay, let's look at a very simple example. Let's take the previous network that we considered here. Right, so this is my network. And I'm going to apply another activation function on top of y. So I'm going to apply a nonlinear activation function. Let's say phi on top of my y. So here the functions that we are going to get is going to be in the form of w and x. Will be, let's say phi is the new function that I'm applying at the end to the output of my network. I1 to m, I have vi sigma wi times x. Right, so this is another neural network when we are applying an activation function to the output node. All right, so here, with the same argument, we can do the analysis of the tangent kernel and the Hessian. And we can observe the following. Okay, so as before, tangent kernel is going to be order 1. Right? So it really doesn't matter, if I'm applying a new activation function here. But surprisingly, remember my Hessian was going to 0 by the rate of 1 over square root of m. Because of this function phi, I'm not going to have that. So my Hessian is also going to be order 1. And you can see that because of the chain rule here. So I'll have a term that would depend on the gradient on the Hessian. And since the gradient doesn't go to 0, then my Hessian won't go to 0 as well because of this phi function, if this phi function, if the phi double prime is not 0, right? So the caveat here is that if phi double prime is not 0. If phi double prime is 0, it means it's a linear function, so it won't change the argument. So if it is non-zero, my Hessian won't go to 0, even if my m, the number of parameters, is large. So this means then I cannot use the Hessian control. So Hessian control fails, right? So my model is not going to be linear. So my model in the limit as m goes to infinity is not going to approach to a linear model, right? So I cannot use linearization arguments in order to talk about the convergence of my gradient descent. But the PL condition is in fact a more stronger. So remember, we use these Hessian controlling in order to say, okay, my PL, if it is bounded, then at my initialization, then I can have a bound on the ball around my initialization. But that's just one way to think about it. Right? If there are some other ways to have a bound on my PL, then I should use it. And in fact, here, yes, there is a way of bounding the PL using the decomposition, using the composition of the function. Right? So if there is a very simple lemma, you can prove it in one line. If your function is mu PL, let's say in a ball around your input, then if you are composing with another function, let's say with a phi, this is going to be mu rho squared PL, where rho is a bound on the derivatives of phi prime. So if the derivatives are above rho, then this phi composed with f is mu rho squared. So now you can see why the PL condition is very powerful, because even though I cannot use the PL control on the function, the newer function that I have with a nonlinear activation at the end, I know f has this PL condition using the Hessian control, but I know phi composed with f, I cannot use it, but I can use this lemma and show that basically if I apply gradient descent on the function g, I'll have a convergence rate that will depend on my learning rate and my new PL condition, which is mu rho squared. Right? So I can show the convergence here. Gradient descent converges in this case, even though my model, so this is very, very important, my model does not go to a linear model. Right? So in many of recent overparameterization results, they use the fact that model goes to linear models, and that's like kind of intuitively obvious why I have the convergence. But here we don't have that. So in a way, the takeaway message that we want to have from these two lectures is that overparameterization is not leading to linearization, right? So that's a little bit more powerful assumption that we need. So overparameterization leads to good conditioning. So you can show these conditioning in one way or the other, or maybe you can come up with a better way to understand conditioning of overparameterized nonlinear systems, but it is not linearization. And the good conditioning basically leads to the PL, and this leads to the convergence of gradient descent or stochastic gradient descent. So that's roughly speaking the takeaway messages that I want you to take from the last two lectures. So before I take your questions, I'm not going to be able to cover the other papers. So there are a lot of very interesting papers. So one paper I posted by Simons Du and collaborators published, I think, in 2019. They also talk about over-parameterization. There are many other interesting papers we posted in the resource section in our course webpage that you can take a look into that. But as I mentioned, here we want to, provide like a big picture of how these techniques are working out. Some of them, in fact, they leverage linearization, but what I want you to keep in mind is that over-parameterization is more powerful than just linearization. So over-parameterization is about getting a good conditioning number and having a bound on the tangent kernel, the minimum eigenvalue of the tangent kernel, that immediately leads to the convergence of gradient descent or stochastic gradient descent. So next lecture, I'm going to talk about the implicit bias of gradient descent or stochastic gradient descent, because you can see that we have potentially infinitely many good solutions when we are using gradient descent. So which of these solutions that we are going to find, and would those solutions have some good biases that may perhaps improve generalization? And that would be a good transition to the generalization lectures and understanding why we have a good generalization, even though the number of parameters can be larger than the number of samples. All right, so with that, let me take questions. So there's a question by Mazda. If the model is sufficiently over-parameterized, but it contains a sharp bottleneck, do our convergence guarantees still hold, or does the bottleneck somehow break one of our conditions? So Mazda, I don't quite understand what you mean by the bottleneck. If you could unmute yourself or clarify it in the message, that would be great.
Sure. So in some of the examples that we were looking at, we kind of assumed uniform width. I suppose we really only looked at like one layer examples, but if instead we had sufficient width and then one of the later layers had a much, much smaller width so that we kind of lose some bandwidth for propagating the information, do we still have that ability to guarantee convergence?
Oh, that's a fantastic question. So the question is that, okay, even most of these analysis, and if you look at the papers that we have posted, they're looking at perhaps like you go to like m neurons and then maybe stay as m neurons, and at the very end you basically shrink the dimensionality of your embeddings. So the question is that what if, like, say, if you have like some autoencoder type architecture, right? So you go to some smaller layers and then perhaps expand. I actually don't know. So that may be the case that in that case over parameterization may not lead to a good conditioning number. So it would be nice to do some experiments and see if in fact that's the case. So most of the practical deep learning architectures, they don't have such bottlenecks, especially early on in the layer. So maybe that's one reason that in practice we don't have those bottlenecks in the architectures. That's a very good question. Okay. Great. So any other questions?